So we're finding the root, or we're finding the x-intercept, or whatever you want to call it, finding the root of the x-intercept. And we want a decimal approximation for that. Now we know what that value is, right? If I were to set this equal to 0, we have x to the 5th equals 3, or x equals the 5th root of 3. And so on the homework assignment for Newton's method, but I think I already put it up, you might see somewhere I ask you to like approximate some value similar to this. Well, this is how you do it, is you write out an equation like x to the 5th minus 3 equals 0, and then you find the root of that using Newton's method. So we know that f of 1 is what?
-2.
Yeah, -2. And we know that f of 2 is
29.
29. That's right. And since we know that this is a polynomial, which means that the function's continuous for all real numbers, then it must cross through the x-axis somewhere between 1 and 2, because the y values went from a negative to a positive. True? Yeah. IVT says a good place to start would be, where do we want to start with? Maybe 1.5? Sound good? Good place to start?
Great place.
All right. So before we can do this, we need to write out the actual formula for Newton's method. So that'll be, I'll write it over here, x sub n plus 1. So the next guess after x sub 0 ought to be x sub n minus f of x sub n. So x sub n to the 5th minus 3 over the derivative of that, which is 5x sub n to the 4th. Good or no?
Good.
All right. And because I still unfortunately can't get my calculator to work on here, I'll just write out what you should be typing in. What should we be typing in? Anywhere we see an x sub n, we should replace it with
1.5 or the answer key, or the answer button.
Answer key, the answer button. So we're going to type 1.5, enter first, and then we're going to replace the x sub n's with answer. So answer minus parenthesis, answer to the 5th minus 3, parenthesis, divided by parenthesis, 5, answer to the 4th, parenthesis. And you'll just keep hitting enter a bunch of times, noting each value along the way. So what is x sub 1? Or are you guys still typing that in?
$1.319.
1.319.
3185185.
31851. Probably just repeating that 319. Yeah, okay. All right, cool. What about x sub 2?
$1.253335.
3335?
Yes.
That's it? Only 6 decimals?
751.
751. Okay. And the next one?
1.245. 822.
822?
6. Yep.
822. Okay.
6. Yeah. 668.
Okay. And the next one? Hopefully it's 1.24, otherwise I'm gonna have to go back and erase that. But
573.
573.
0953.
All right. What about the next one? Is it gonna be the same?
No, 1.245.
I'm getting tired of writing these down now. We better be getting close.
73094. That's all.
All right. And then the next one is the same, I hope.
Yes.
All right. Great. So we'll say that is good enough right there. Okay. As soon as it starts repeating, we've reached a point where our accuracy is the best we can get using our calculator. Good or no?
When
Do you
we're
want us to show every single x value, or can we just show the ending one?
I'd like you to show the ones in the middle. Yeah. Yeah. Just so I know that you did it that way and didn't actually like just go in and have the calculator approximate it for you to begin with, like from the graph or something, which we haven't really talked much about how to do that because my graphing calculator won't work. So we'll have to do that once I fix my graphing calculator on here. But yeah, show them all. Let's do one more. Let's find the intersection point of, let's see, what's a good couple of functions? Anybody got a function they particularly like?
x squared is really cool.
No. I don't think so. Let's go with, that's too easy of ones. We can't do that. Let's go with, let's find the intersection point of y equals x cubed minus 5x. Oh, somebody has suggested things in sine or cosine. Okay. All right. Let's do a sine or a cosine one. How about y equals x cubed minus 5x and y equals sine x plus 6. So we want to find the intersection point of those two functions. So when do two functions intersect with each other? They intersect each other when
Their x's and y's are equal.
Yeah, when their x's and their y's are equal. So if this is y equals and y equals, just set them equal to each other. Sine x plus 6 equals x cubed minus 5x. And then now to figure out when they intersect each other, we have to figure out when that's true, which means we have to solve for x. And to solve for x for anything, the easiest way usually is to get it all to one side. So we'll have x cubed minus 5x minus sine x minus 6 equals 0. And so now effectively all we're really trying to do is find the x-intercept of this new function, x cubed minus 5x minus sine x minus 6. And might be a little bit of a pain to figure out where to start with that, but we'll come up with something at least, hopefully. What is our x sub n plus 1 going to equal? What is our Newton's method formula going to be? It's going to be x sub n minus what's going to be in the numerator?
X sub n cubed minus 5x sub n minus sine x sub n minus 6.
Perfect. And in the denominator, we should have the derivative of that. So 3x sub n squared minus 5 minus cosine x sub n. And let's see, where do we think is a good place to start here on this? Anybody have a guess for the first value you want to use? Just for a second, let's ignore the sine x, because that's always going to be between 1 and -1. That's not going to affect it too much. What's a value that I could plug in that would make this thing negative? And something that I would plug in that would make it positive without the sine x. I think 3 would make this positive, right? 27 minus 15 minus 6 equals negative 6, right? 3 would make that thing, equals positive 6. 3 would make this thing positive because the minus sine x is only going to be somewhere between negative 1 and 1, and so that'll still be positive. But 2, 8 minus 10 minus 6 is going to be negative 8, and this plus or minus 1 is not going to affect it too much, right? So between 2 and 3, it looks like that's where it's going to cross through the x-axis. So let's pick something between 2 and 3. How about 2.5?
Perfect.
Great. And you're going to type in answer minus parenthesis, parenthesis, answer cubed minus 5 answer minus sine answer minus 6 over 3 answer squared minus 5 minus cosine answer. And what do we get? X sub 1 should be, let's hope this works out nicely. 2 point something, I bet. Make sure you're in radians also. Because of the trig functions, otherwise it's going to get screwed up.
Seven 3 8 7 0 7 8 4 6.
I've missed one. 7 3 8 7 what?
0 7 8 4 6.
The 0 before this 7?
No, you're good.
0 7 8 4 6. Okay.
Yes.
And what's the second one?
It's actually 713.
Second one is?
Yes.
All right. Good thing I had room for that. 713.
9 4 7 5 4 6.
All right, and then just I'm gonna not write the rest, but you guys will until you get down to what? When does it become the same twice in a row?
2.713.
2.713,
661.
661,
811.
811. Cool. So pretty cool, really, that you can find essentially a really good decimal approximation for the x-intercept of basically any function that you want to, or you can find the intersection point of basically any two functions that you might want to. Pretty cool, huh? No?
Yes.
Yeah. All right. Does that all make sense there? Are we all good there now on Newton's method, we think? Everybody feel all right about Newton's method?
Yeah.
Yeah? Nobody has any issues? Everyone's good? Don't need to go through it any further? All right. Spectacular. Let's move on then to something new. Let's move on to something called optimization problems. Optimization problems are just another application of our derivatives. So an optimization problem is something where we are looking for the maximum or for the minimum of something, right? So suppose I have some word problem and the situation is I am looking for the maximum profit given some price. That'd be an optimization problem, right? Or if I'm looking for the minimum cost for me to do whatever I'm trying to do, that would be an optimization problem. Or I'm looking for the maximum volume that a container could have given some other constraints, that's an optimization problem. If I'm looking for the minimum amount of material to use to create something given some situation that I'm looking at, that's an optimization problem. Anytime we're looking for, in a real world situation, a max or a min of something, it's an optimization problem. And the calculus part of it is really easy. Calculus part is just taking the equation that you have, taking its derivative and finding when it has a max or a min, right? Which we've done a lot of already, haven't we?
Yep.
Yeah, so that part's pretty easy. The part where this gets difficult is you will not be given generally the equation that you need to take the derivative of. You're going to have to write that yourself based on the word problem. That's where people start to struggle. It's not with calculus, it's with the coming up with the equation. So these are the steps that we will generally want to take for any optimization problem. First off, read the problem. If you don't understand what's going in the problem, read it again and 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 again until you understand what is being asked of you in the problem. Then draw a picture. Okay? Generally, a picture is going to be exceptionally helpful to you in this. So draw yourself a picture and then label that picture, write yourself an equation, and for step 4, either graph the equation to help you find its domain, or if you can, just kind of figure out what the domain of the function is itself, so that when you do take the derivative and get the max and the min, you can make sure that your answer makes sense in the context of the problem, right? Because if the result you get is outside the domain, then obviously your answer is either wrong or not an answer. So once we get our function written, we will take its derivative, find the critical values, and look at the endpoints and see which one is the max and what's the min. Good or no?
Good.
Good.
All right. Let's give this a try. It's going to make more sense once we start doing it, I think. So we want to find the point on the graph of y equals x squared plus 1 that is closest to the point 3, 1. So what is this asking us to do? Do you understand what it's asking, or do you need to reread it 7 times?
It's basically asking us to find, I don't know, it's kind of self-explanatory what it said. Yeah, like which point is the closest distance to point 3, 1, even though 3, 1 isn't a point on there.
All right, 3, 1, we'll call this, let's see, 1, 2, 3, 1. 3, 1 is not a point on our parabola, right? But some point on our parabola, y equals x squared plus 1, is closer than every other point on the parabola to that point. So we are trying to figure out when what is at a minimum.
Distance.
This distance. We want to know when is this distance between this parabola and this point at a minimum. That's what we want. So let's see how we've done with our steps so far. Number one, we've read, we understand what's being asked. We drew a picture. Yeah. I didn't quite label it with variables yet. Let's label it with everything we can. So there's a variable, the x-axis, that's the y-axis. This is the function y equals x squared plus 1. We've got some point here, which we've got labeled as 3, 1. And we've got some other point here, which ought to be labeled as, how could we label that point?
X1, Y1.
Okay, it's x and y, right? We'll just label it as x and y for right now. And we want to know when is that distance a minimum. So what's the distance between those 2 points, between 3, 1 and x, y? That's the part where we're going to now write an equation. So what's our distance between x and y? Distance ought to be how do you find the distance between 2 points?
Distance formula.
The distance formula, the square root of x2 minus x1. So that'd be, how about x minus 3 squared plus y minus 1 squared. Good or no? All right, so what's wrong with this distance equation that we've got here? I mean, there's nothing wrong with it, but what's causing a problem with it?
We have 3 variables.
Yeah, we got 2 different variables. So is there a way to get rid of the y variable, let's say?
Substitute it with the with the function.
Yeah, the function itself is y equals x squared plus 1. Right, so if y is x squared plus 1, we should be able to rewrite this as distance equals the square root of x minus 3 squared plus x squared plus 1 minus 1 squared. And we should then be able to simplify that all the way down here to the distance is the square root of x squared plus 1 minus 1 is just x squared, right? And if you square that, that'll be x to the 4th plus x squared minus 6x plus 9. Good or no?
Good.
Cool. All right. So we now have, let's see, let's look at our steps here. We've read it, we've drawn our picture, we've labeled it, we've written our equation. We didn't graph our equation, and we also didn't identify its domain. So this step right here is sometimes a little bit questionable. Sometimes you don't need to graph it or even really look for the domain. You can just, once you get your answer, see what makes sense in the context of the problem. And finding the domain of this function, you know, the square root of x to the 4th plus x squared minus 6x plus 9 might be a little bit irritating without actually graphing that equation. So if you wanted to, if you had a calculator, you could graph it and see what the domain was. But I think we're going to skip that step right here and move on to the next one, which is determine which variable is to be maximized or minimized. I think we know that, right? Which one do we need to minimize? The distance, right? We want to know when is distance at a minimum. So we know we want to minimize distance, and it says write that as a function of one variable. Well, we've done that. So we're all the way up to number 6. We now need to find the critical value, and we need to find any endpoints. And so let's first work on critical values. How do we find critical values?
When it's equal to 0 and when it's undefined.
When its derivative is, right? So we need a derivative.
Oh, yeah.
1 over 2 root x to the 4th plus x squared minus 6x plus 9 times the derivative of x to the fourth plus x squared minus 6x plus 9, which is 4x cubed plus 2x minus 6. Yeah. Good or no?
Good.
Okay, cool. So from there, first off, when is it undefined? Well, it would be undefined. I'm going to write this down here. D prime is undefined if the denominator equals 0. True?
Yeah.
If the denominator equals 0, that 2 doesn't really matter. It's the square root of x to the fourth plus x squared minus 6x plus 9 that would equal 0, right? Which is the same as our original distance function, isn't it? So our derivative is undefined at any x values that would make the distance equal 0. Are there any values that make the distance between 3, 1 and the parabola 0?
No.
No, because this point is not on the parabola. If this point was on the parabola, then there would be a point that made the distance 0, but there is not. So we can ignore this because it would make, because then d equals 0, and we know that d cannot equal 0, right, in the context of this particular problem. Everybody okay with that?
Yeah.
All right, so now we want to know when does d prime equal 0. So that's when does 4x cubed plus 2x minus 6 equals 0. And how do we first off simplify this? Probably into 2x cubed plus x minus 3 equals 0. And now we need to find a way to factor this. What's the best way to factor a cubic that's clearly not able to be factored by grouping?
Synthetic division.
Synthetic division. And how do we know what values to try? So then some of that stuff I posted at the very beginning of the year. Using the rational root theorem, right? Using the rational root theorem, we look at the factors of the constant. So that'd be plus or minus 1 and plus or minus 3. And divide them by the factors of the leading coefficient, plus or minus 1 and plus or minus 2. So 1 over 1, 1 over 2, 3 over 1, and 3 over 2 are all the different possibilities for a value that could factor evenly into this. Hold on one second. Okay, sorry about that. So the values that we want to check are either 1 divided by 1, 3 divided by 1, 1 divided by 2, or 3 divided by 2. So which one seems like a good one? We could do plus or minus.
1.
Yeah, 1 seems like a good one, probably because we recognize that if we plug 1 into this, it does come out to be 0. So let's plug in 1 into synthetic division. So 2 for 2x cubed, 0x squared, 1x, and negative 3. So bring down the 2, multiply by 1, add the 2, multiply, add, multiply, and add. And this should tell us that 2x cubed plus x minus 3 factors into, we're going to need a new page for this. It's going to factor into x minus 1, because that's from the 1 that we used, and then 2x squared plus 2x plus 3. And so now we've got to see when does that equal 0. And first off, x equals 1. And second of all, we got to do this part, which if you remember back from like algebra 1, right, the discriminant b squared minus 4 times a times c, this value 4 minus, what is that? 4 minus 24, right? That's negative 20. And so if the discriminant, if b squared minus 4ac is less than 0, that quadratic has no real solutions. So the only value we get is x equals 1. Good or no?
Good.
All right, so we'll make a sign chart. And our derivative was, what was it? It was, well, I don't remember. What was our derivative? It was 4x cubed plus 2x minus 6 over 2 times the square root of something, right? The square root of something is always going to be a positive number. So this denominator is always going to be positive. So really when I plug stuff in, I'm really just looking at the numerator. So if I plug in 0, the numerator is negative. So it's decreasing. And if I plug in something more than 1, like 1,000, this is clearly positive. So our function is then increasing. And so we would note then that this has a minimum at x equals 1, which tells us that we have a minimum distance at x equals 1. And so the point at x equals 1 on x squared plus 1, f of 1, ought to be 2. So the point 1, 2 is where that minimum distance occurs. And I think, it just asked us to find the point. So that's our answer, 1, 2. If it asks us to find the minimum distance, then we could go back in and plug 1 into this, and we'd find out that that distance is 1 plus 1 is 2, minus 6 is negative 4, plus 9 is 5. Inside of the square root, the distance would be the square root of 5 units away. And that's the minimum distance. Does that make sense?
Yep.
Go to the next page for a little bit, please.
Yeah, definitely. And then I still have one thing I want to talk about with this. Once you take a minute to look at that, and then I want to talk about something else with it.
So we found that there's a minimum at x equals 1, and so we use that minimum at x equals 1 with the original equation to get the point 1, 2.
Correct. Yeah, that's what we got f of 1. Yep. But yeah, back here with y of 1 or f of 1, right? There's our function. 1 squared plus 1 gave us 2. So 1, 2. Good or no? All right, so I want to make one other point about this. And we had one second. Okay, sorry about that. So we had distance equals this, square root of x to the 4th plus x squared minus 6x plus 9. Okay, so x to the fourth plus x squared minus 6x plus 9 inside the square root. When you are looking for the minimum of a square root of something, so if we're looking for the minimum of the square root of something, this will occur at the same x value as the minimum of that thing squared. So this will occur at the same min or max. So we could say max or a min as that thing squared. We'll say as the square root of that thing squared. So if we wanted to make our lives a little easier, we could have said d squared equals x to the fourth plus x squared minus 6x plus 9. And then we could take the derivative of both sides of that. And then our derivative itself is much easier, right? It's just the 4x cubed plus 2x minus 6. We don't have to worry about this square root of a bunch of garbage in the denominator. So sometimes this little trick here will help you. It didn't really make this particular problem a lot easier, but there are some where it can make it quite a bit easier. So if it's easier to take the derivative of the square of your function, you can do that to find the same x value for that same max or min for the different functions. Does that make sense? Or no?
Yes.
Okay. But if you factored this, you still would have got x equals 1, right? Because that's what we ended up factoring anyway back here to get x equals 1. Cool. All right. Let's do another one.
1 second. For this method, though, sometimes it can be really weird, right? Because you can get some really annoying square root.
Well, yeah. So suppose we have a really annoying square root here, which we sort of do. Rather than deal with the annoying square root, we just square it and get rid of the square root completely. So we can just basically ignore the square root. You just need to show that that's what you're doing.
I'm talking about for the answer. If we get like the square root of 2, would it just be left as the square root of 2, or would we get the decimal?
Oh, yeah. Just leave it as an exact value, unless I tell you to.
And then you would square it. And that, okay. We're good.
Okay. Cool. Any issues? Everybody all right? All right. Let's take a look at another one. This one's a little bit more difficult and it's going to require us to use a calculator. So if you don't have a calculator with you, go grab a calculator. We're going to inscribe a rectangle underneath one arch of the sine curve and try to figure out what the largest area that rectangle could have is. So let's try and sketch a picture here real quick. Here's one arch of a sine curve, right? It's going to look something like this. There's one arch of it, and to inscribe something under it means to draw it between the x-axis and that curve, which means that when I draw that rectangle in there, it's going to have one vertice and another vertice that touch the sine curve, and then it's just going to be a rectangle otherwise, just like that, down on the x-axis. Good or no?
Good.
All right, and so we want to know what's the largest area that rectangle could have for just the basic sine curve. Because I could draw a lot of different rectangles that looked like this, right? Can I draw one that looked like this? That rectangle would meet those criteria, wouldn't it?
Yes.
Yep.
Yeah. Which one's got a bigger area? Well, I don't know. Probably looks maybe like the red one, but it's kind of hard to tell. What if I drew it like this? Which one's got a bigger area? The red one, the blue one, the green one? It's kind of hard to tell, right? There are an infinite number of different ways for you to draw a rectangle inside the sine curve. So we want to figure out which one of those has the largest area of all the possibilities. So let's label our picture as best we can. Here's our x-axis, here's our y-axis. Here's our function y equals sine x. And what else can we label on here? What are some other things we know? Where does sine x cross through the x-axis? Part at pi. So that's one thing we can label. What else can we label on here? Anything else?
The height is 1. The peak of the height.
This height up here, the highest point we go up to here is at 1. Okay, good. All right. I think that's about all we could probably label right off the bat. So we could label two things on our rectangle, right? The two important things we need to label on a rectangle are a length, right? And a height, or a base and a height, or a width and a height, or a length and a width, or whatever you want to call them, right?
Yeah.
Okay, so in order to find the area of this rectangle, we got to multiply the length times the height. So we need to write an equation to represent the length and to represent the height. Sorry about that. All right, so we need the length and height. So how are we going to write out this length and this height?
If I recall correctly, the largest area a rectangle can have is when like both sides are the exact same. So maybe L equals H.
Well, that's, I mean, that is true for just in general. You know, if you tried to just draw a rectangle that had to have a certain side length, right? The biggest area would come from a square, but I can't, the square that I would draw in here would be more like this. And that doesn't necessarily mean that that's the largest that I could possibly do within this situation, within this sine curve where it has to touch these vertices up here. So we can't be guaranteed that a square is the largest that I could inscribe into this. Like, for example, suppose I was looking at doing this into something like a parabola that was very wide opening. Would a square that I sketched underneath this curve, right, this is the square I could sketch, or that's not really a square, but
Oh,
like
yeah.
that square is not going to have the largest area of any rectangle that I could draw underneath this thing. So while you're right about the fact that the square is the rectangle of largest area, it's not necessarily the thing of largest area that can fit underneath this particular function.
All right.
So let's try and get some stuff in here in terms of x. Where is x? I mean, x is our x-axis. How do I measure an x value on the axis? I start where? Should start at the origin, right? And go out to somewhere out here. Where do we want x to be? From here to here? From here to here? From here to the middle? Where do you want x to be?
To the closest vertex.
Closest vertex, okay. So let's call this x. If I call this x, then what's the value of this point? This point would be the point x comma what?
F of x1.
F of x, right, which is,
Y. So sine x.
which would be sine x. So this would be the point x comma sine x. So what's the height then of this rectangle? Based on where I put x right there.
Sine x.
Height must be sine x. Good. Okay. Well, if we're talking about a sine curve, right? Sine curve goes from here to here. What can you tell me about it? Is it symmetric?
Yes.
Yes. So if this distance here is a distance of x, what can you tell me about that distance also?
It's x.
X.
Also x. So, well then, what is the length equal to?
2x or pi minus 2x.
Pi minus 2x, because that entire length from 0 to this x-intercept is pi. We've knocked off 2 x's. So we've got a length of pi minus 2x, the height of sine x. So our area is just pi minus 2x times sine x. Everybody good with that?
Yeah.
Cool. Let's think about the domain of this. X needs to be at least 0, right? X has got to be more than 0. We got to go over somewhere to get a rectangle. So we know that X is greater than 0. What's the largest value that X could be? I could go over almost to the middle, right, of my X, because I have to have another X on the other side.
Pi halves.
Yeah, so the most we could go would be just before we got to pi over 2. So this is our domain for like step 4 or whatever of those list of steps that I gave you. So our domain is X has to be between 0 and pi over 2. So when we look for our derivative and we find places where the derivative is 0 and when the derivative is undefined, we only want to choose values that are between 0 and pi over 2. Good or no?
Good.
All right, cool. So now we've got, let's see, if we look back at our steps way back here, have we read and figured out what we're trying to do? Yeah. Did we draw a picture and label it? Yeah. We write an equation? Yeah. Did we find the domain of that equation? Yeah. Did we determine which variable we need to maximize or minimize? Yeah, area. Did we write our equation as a function of that variable? Yeah, it's area all in terms of X. So now we just need to do the easy part, find the critical values and determine the extrema. Good or no?
Good.
All right, so what's A prime? Well, this is pi minus 2x times sine x. That's product rule, pi minus 2x times cosine x plus sine x times the derivative of this, which is -2. Good or no?
Good.
All right, now I think that this is not going to be super easy for us to find the values at which this equals 0. Now, obviously, we could use Newton's method to approximate the zeros of this, but I think it'll probably just be easier if we use our graphing calculator. And since I don't have a functioning graphing calculator on my computer, I'm just going to use Desmos for it. Desmos will give us a nice approximation. So we had what, pi minus 2x times cosine x. And then we had plus, what did we have? We had sine x times -2. Is that right?
Yep.
Okay. So we know that x needs to be between 0 and pi over 2, right? So any of these negative values we can just ignore. Here's a value, 0.71. It's 0.71 between 0 and pi over 2.
Yes.
Yep, so we can use that one. And what about this one, 2.431? Is that between 0 and pi over 2?
No.
No, pi over 2 is, what, a little over 1.5. So nope. And all of these ones are also out of there. So this one is the only value we get. So according to Desmos, this happens when x is approximately 0.71. Now, normally, we would use our graphing calculator to do this, and we get like a full long value that's like 6 or 7 decimals at least. And we would use that value for all of our other calculations, and we would only round at the end. And when we would round, we'd round to 3 decimals. But we're going to have lots of practice with that before the AP test, once I get my graphing calculator on the computer working again. So for now, we're just going to stick with x is about 0.71. And we should really easily be able to figure out our sign chart for this, because we're sitting here looking at the graph, right? We're looking at the graph of the derivative. To the left of 0.71, the derivative is positive, isn't it?
Yes.
And to the right of 0.71, the derivative all the way till pi over 2 is negative. So our derivative goes from positive to negative, telling us the function goes from increasing to decreasing, telling us that we have a max at 0.71. Right? And so x is 0.71, gives us a max. And if we wanted to find the height and the length of that, we would just plug 0.71 into each of these. And if we wanted to find the area, we would just multiply those two things together. So what's the height? What's the sine of 0.71?
How many decimals do you want?
Just give me 3 for now, I guess.
652. 0.652.
All right. What about pi minus 2 times 0.71? What's our length?
$1.722.
And multiply those together. What's our area?
$1.227.
1.227. Great. And if you had units here, you'd attach units to it, but we don't seem to have units, so good enough. Good or no?
Conceptually good.
Conceptually good, yeah. Could you do it on your own? Good question. Yeah, that's what we'll find out when I post the homework assignment on this. But we're gonna do some more for some more practice. Because these are just the easy ones here. Let's take a look at another one. So I'll give you guys a second to read through that, and then we'll start talking about it. All right, everybody read that and have a general idea of what we're trying to do?
Yeah.
Okay. So let's draw what we got. We got this sheet here. We're going to cut the corners of it off, right? It starts off being 25 by 20. True?
True.
And we're going to cut these corners off. And how much do we cut off from each corner? Cut off X from each corner, right?
Yes.
Okay. So now we're sitting here looking at something like this. And we're going to fold right along these lines up so that we get a box, right? If we fold each of those 4 little flaps up, we're going to get a little box that has an open top to it, right? No top on it. Good?
Good.
So we've got our picture. Perfect. We want to find the volume. Well, what's the volume of a box? It should be length times width times height. So what's the length?
20 minus 2x times 25 minus 2x times x.
All right. So our length and our width are 20 minus 2x and 25 minus 2x because we've chopped x off from each of those sides, right? So subtract an x and subtract an x from both the 25 and the 20. And then our height is just whatever the amount that we chopped off is because we have folded that flap up. So we got 20 minus 2x, 25 minus 2x, and x. Everybody good with that or no?
Yeah.
All right. Let's simplify that out. Negative 2x times negative 2x is 4x squared times an x is 4x cubed. And then 25 times negative 2 is negative 50x, and then a negative 40x, that should be negative 90x. And then times x is 90x squared. And then we got a 20 times a 25, which ought to be 500x. And now we just need, now that we've got, if we look back at all of our steps, we've read it, we've drawn our picture, we've written our equation. We didn't necessarily graph our equation to find its domain yet, but we'll do that in a second. So that'll be our next step. And then we want to determine what we're going to max or min. So what's the domain here? What's the smallest x could be? X needs to be greater than what? Yeah, we got to cut off something. So x has got to be greater than 0. What's the most we could almost cut off?
10, right?
10, right? Because we got to cut off 2x from 20. If I cut off 10, that cuts off the entire side, right? So we got to cut off less than 10. So our x value is going to be between 0 and 10. And now we're done with steps 4 and 5. We've gotten volume, what we're trying to maximize, written all in terms of one variable, and we know the domain that we're looking for it on. So we're up to finding critical values and endpoints. There's no endpoint here because 0 and 10 are not closed values. So we'll take our derivative. V prime equals 12x squared minus 180x plus 500. And we want to know, first off, is this undefined ever? No. So we'll just look for when is it equal to 0. And I believe we can divide everything in there by 4. So this will give us 3x squared minus 45x plus 125 equals 0. And from there, I think we probably going to have to use the quadratic formula. So x equals 45 plus or minus the square root of negative 45 squared minus 4 times 3 times 125 all over 6. And what does that give us? 45 plus or minus the square root of what over 6?
$525.
All right, and let's see, can we take something out of that 525? We can take a 25 out of there, right? So that would be, I guess I'll go to the next page. This will be 45 plus or minus 5 root 21 over 6. Good or no?
Good.
All right. Spectacular. So, do we want the plus or do we want the minus?
Plus.
Really? Let's look at Desmos. 45 plus 5 square root 21. If I take that and divide it by 6, that's 11.3. Is that within our domain?
No.
No, so we actually need the minus 3.6811869208.7. Yeah? Right there. So we'll use the minus because plus is not in the domain. So we've got 45 minus 5 root 21 over 6. And if we were to make our sign chart with that value, if I plug in something more than, what did we say that was, 3 point something? So if I plug in something more than 3, like 4 or 9 or whatever, 9, let's say, into our derivative, we're going to get out a negative number, right? Because we're going to have something like, let's say, 81 times 3 is 243 minus 9 times 45. That's a pretty darn big number, right? That's what, a little over 400. And then we're going to add 125 to it. That's still going to stay negative. So we're going to have a negative here. And if we plug in something less than that number, like 1, we'll have 3 minus 45 plus 125, which is positive. So we end up with a maximum volume when x is this value. And I think it asked what the max volume is. You could plug that in. I'm not going to spend our time right now since we're almost out of time. But you just plug that x value into your volume equation and get an answer. Good or no?
Good.
Cool. All right. That is it for today. I don't think we have time to do any more optimization yet. We got 2 or 3 more here. Looks like 3 more of these to do tomorrow. And then we're going to talk about another thing called related rates, and then we'll be done with applications of the derivative.